I don't understand what's going on. Let's try one more time. Can you see it?
Yeah, now it's good.
It's good now, yeah?
Yeah, Netflix challenge.
Yeah. All right, so let's cross our fingers and try to continue. And if it does not work, then I will do without animation. Anyway, so it's metric. As I said, it's Netflix challenge. You want to complete your metric so that it will have lower rank. So can you see the completion? Box.
Yeah.
Huh?
We cannot hear you now.
We have Netflix challenge slide.
Can you now see entries? Can you see entries?
Yeah.
So new line. Can you see new line on the bottom?
Yes. Very
okay, good.
This one.
Yeah. All right. So it's I don't know what it was. So anyway, here it is obvious how to do it, but in general, it's very difficult computational problem, and there are really hundreds of papers how to do it. And usually, when you do it, then you replace this discrete approximation like rank with something like trace norm, and the best algorithms are indeed based on trace norm. You try to minimize.
May I ask, sorry about this?
Absolutely. We have lots of time, Boris.
They mimic compressed sensing in solving this.
Yeah. It's one of the techniques. Yeah. Lots of stuff into this innocent problem, and so compressed sensing is one kind of algorithm. So you can try to minimize trace norm. It's convex optimization. Lots of stuff. So, and it was just for an introduction, because what we are going to study today is a slightly different model, not very much different, but still somewhat different. So it is matrix rigidity, and it was introduced independently by Valiant and Grigoryev long ago.
We have Netflix challenge slide still.
Even now, yeah?
Yeah.
Okay, let's forget about our animation. Let's go.
Yeah, it's okay now. Now it's okay.
No, yeah, it's okay. But I also have some animation on my slides, but let's forget about it. All right, good. So this definition was given by Valiant and Grigoryev long ago, and it's very simple, very natural. Actually, Yuri already gave it. So we fix a field. Any questions? We fix a field and we fix a matrix A. Well, it need not be necessarily square, or it need not necessarily be square, but let's assume that it's square for simplicity. And also we have, let's fix a parameter R, and let's assume that it's at most n over 2. We are not interested in this range. And the rigidity function, which is denoted like that, and sometimes I use key to denote the ground fields. Sometimes it will be important, is simply defined as the number of changes. I use this notation, zero norm, which is the number of non-zero entries. The minimum number of changes that you have to do to your matrix A, so that you reduce its rank below R. So as you can see, it is very similar to Netflix challenge. The main difference is, first of all, that we want to correct entry, not just make, we have no stars. Now my matrix A is fully defined, and we have to changes instead of completion, change some entries. And what is more important, and what makes this problem even more difficult, is that we don't specify the positions of the changes. We just have a budget on them. And that's the definition. Let me very briefly go into some motivations. Why do we care about it? I mean complexity theories. The first motivation is original motivation by Valiant. So it turns out that we are, in terms, as many of you know, in terms of proving circuit lower bounds, Boolean complexity, we are really miserable. And the next talk by Volodya Podolsky will be devoted to this topic. And we really don't know our strong lower bounds for circuits. And on this slide, I tried to show how exactly miserable we are. So we look at as simple model as possible. We have a field K, whatever you want, or G of 2, or the reals, and we consider circuits that allow only linear operations like this. So, and we want to compute a matrix A. Now we view it as a bunch of linear forms by linear mapping, bunch of linear forms. We want to compute all those linear forms using our operations, and I put also all possible kinds of restrictions. I require that the number of operations, the size is linear, and also depth, which is essentially the length of the longest path in my circuit, is logarithmic. So all the restrictions you can put in. And this open problem, it is open, it has been open for 50 years or something like that, and we really don't have any clue how to solve it. But turns out that that's why rigidity was essentially invented by Les Valiant. Turns out that if we have sufficiently good lower bounds on rigidity, then this matrix A indeed cannot be computed in this model. This matrix A is hard for our model. So, and question. And one remark that that is the same throughout my whole talk, that we of course mean asymptotics here. I may write a single matrix A, but what we actually mean a sequence of matrices, and n grows to infinity, and we look at the asymptotics. And also let us understand, for the purpose of calibration, let us understand what can we expect from this quantity. Turns out that it is always linear. No, if A has full rank, then it is at least n over 2, just because if you want to reduce the rank of your matrix to n over 2, then you have to change at least one entry in at least n over 2, say, columns, right? So this is a trivial bound, and you just want to improve it by this epsilon, and then you will solve this major open problem in circuit complexity. Another motivation, it comes from my paper. So we've already seen communication complexity in Yuri's talk. So now I would like to slightly change the notation. Namely, I will denote the size of my matrix as capital N instead of lowercase n, and lower n case will be the number of bits. The idea is that Alice or N holds the name of a row encoded by that many bits. Bob holds a column, and I want to compute the entry of this matrix. That's the standard model that we've seen in Yuri's talk, standard communication complexity. I don't apply here any randomization. Instead, turns out that you can connect this model, and it gives really nice connections to computational complexity theory, because in computational complexity, we have this polynomial hierarchy, PH, which is the standard class polynomial time computable functions. If you put existential quantifier in front of it, then you get NP. You put universal quantifier in front of it, you get what is called core NP, and you can alternate the number of quantifiers, and you will get, in computational complexity, you will get very important and widely studied classes. And you can do the same thing in computational complexity. I don't want to go into too many details here, but it is also well-studied model, and we have, as we know from Yuri's talk, we have good lower bounds for ordinary communication complexity, but not for this thing. It is also wide open, and all right, that's what I just said. So Alice and Bob can run communication in as many rounds. So I hope it's right. Yes, it's a sublinear number of rounds, sublinear in n. So and also they have fixed number of alternations. Let me skip the details of them all. Anyway, simplified version of my theorem, it says that if you have lower bounds for rigidity of these matrices, then you know that they are not in this class. That's the second standard motivation to study rigidity. And let us look a bit at the parameters. I don't expect you to read all of them, but if R is of order capital N, then right, the whole thing gets trivial, right? So X and log cancel each other. You get here something less than 1, which is obviously nonsense. So in this for this motivation, we need rigid matrices in very different regime, namely the rank of a rigid matrix or the rigidity, or it should be studied in the regime where the rank of the resulting matrix is much smaller than its size. These are two main motivations. Any questions so far? All right. So and now let us see what we have here. Right. Explicit here in red, and that's what we are interested in communicating in the complexity theory. We are not interested in almost all matrices. We are interested in explicit matrices, but still it is good to know, just to understand what's going on. How does a random matrix behave itself? So, and it was essentially answered in the seminal paper by Valiant. If you look at almost all functions, or almost all matrices, I'm sorry, where almost all, if the field is finite, then it is it's just a counting measure. Actually, for any field, you can take plus minus 1 Rademacher matrices, plus minus 1 random matrix. It also will be random. It also will have high rigidity. If K is infinite, then you simply take the risky random, which means that it's not a root of a finite system of polynomials, etc. So anyway, that's the holy grail, in a sense, that for almost all matrices, you are actually quite rigid. Boris, you are
May I ask a question, Sasha?
Absolutely.
Because Yura sent me the paper by Valiant, but where this definition was introduced, but I didn't find this result there. Are you sure that it's in this paper? You have this?
I think I saw it there some 30 years ago. So let me not make definite claims. But
okay.
at least
just please send me the real paper when it's proved.
I'm not sure I can do it. I think it's a physical preprint which I have in Moscow.
Okay.
So, but I will try to find it. But actually, that's what everyone refers to. Maybe I don't know why.
Okay.
In any case, it's easy.
Mm-hmm.
Right, good. But Borja, he actually had two papers, 76 and 77. Maybe that's a source of confusion.
Yeah.
Right, let's talk offline. So I will try to find it, but yeah, let's talk offline. Anyway, it's easy. I vouch for the result. It's easy. Right. So now we are interested in explicit matrices, and let me immediately introduce the main probably actor in my talk. It's Hadamard matrices. What is Hadamard matrix? It's just plus minus 1 Rademacher matrix that is orthogonal up to a scaling factor, which is obviously square root of. So, and let's for simplicity assume that H is symmetric. It's in combinatorics. It's a very popular theme, and it's major open question for what questions. It's measured theme in combinatorics, major open problems for what values of n does this thing exist. But there is very good example of this matrices that has at least 10 different names. Like any great thing. So here I gave some of them. Anyway, the matrix is very simple. We assume that rows and columns are indexed by elements of a vector space over GF2, and it's the character table defined that. So it's extremely popular matrix, and canonical example, its spectral behavior is as nice as you can think of it. Actually, spectral behavior of any Hadamard matrix is very nice. You know its operator norm, trace norm. You know everything. You may potentially want to know. Frobenius norm, of course, everything. You know everything about these matrices, and it's an extremely popular object in communication complexity, for example. I don't know if Yuri, he talked about unbounded communication complexity, and that's the standard example of a matrix which is hard in that model. Anyway, let me continue with rigidity. So, and for arbitrary Hadamard matrices, there is a variety of methods to prove that they are somewhat rigid. So here I gave a few examples, and the first class of methods are combinatorial methods. Namely, you basically look at how minors of a Hadamard matrix look like, studied the property of its minors. And these are early results. And this, for example, these are combinatorial or semi-combinatorial statements that go into them. So I think I don't have to read them. They are sort of natural. There are also algebraic methods. So also it's from my paper, Sylvester matrices. Again, these are discrete Fourier transform matrices. They are a special case not only of analytical objects which are Hadamard matrices, but you can also view them as character tables, as I said, and you can look at any abelian group. So we want to make sure that it is semi-simple. And then you will get this number, which, as we will see later in my talk, this number is really more or less our barrier that we don't know how to penetrate. So there are many methods. I will show some of them to prove this bound for various classes of matrices, but essentially what we have. And as I said, the proof is very algebraic, and it is based on studying some rank of three tensors, some special rank of three tensors, which you can handle, unlike, as many of you know, we don't know, for example, how to prove lower bounds on matrix multiplication or good lower bounds, but if you sufficiently relax it, then you can. And another class of methods was introduced in our paper with Boris also long ago. So, and it actually, this is probably the closest thing in my talk to the, topic of this workshop, because, everything I know about this sentence I learned from Boris. So maybe I will not comment on it, but the idea is that there is the whole class of results. You take a matrix with, say, orthogonal rows, and you take a random subset of its columns. So what's what will happen, how orthogonal it's going to be, or something like that. So, and that's the novelty in our paper. The novelty in our paper was precisely that we, instead of looking at, where is it? Looking at a fixed minor, no, a fixed minor is here. We looked at randomly chosen minors. And so then there were some simplifications also, so you can get it with simpler methods. But let me skip it. So if we go beyond Hadamard matrices, and actually you can do slightly better. But what is here in the yellow box is the limit of our knowledge. You can shave off another logarithmic factor, which, by the way, will not make sense when R is of order n, because it will give you a new constant. Big omega, if you don't know it, it's a notation which is opposites to big O. It means some epsilon greater than 0. And there are actually several different methods of proving these bounds. These bound ends remarkably, they work differently in the case of finite fields and infinite fields. The methods are different for finite fields. It was proven in this paper. So I guess, as far as I remember it, what you have to do, you have to take a good linear code matrix of a good linear code over GF2, for example, and then it will be sufficiently rigid. If your field is infinite and you have sufficient room, then you can do it even simpler. Namely, you might consider matrices that are called totally regular matrices. So if all square submatrices have full rank, and this is a good example, Cauchy matrices, standard example, turns out that they have full rank. And it is an easy observation. Actually, I hope to have time just to prove it at the end of my talk, that if the matrix A is totally regular, then it is rigid like that, but without logarithm factor. And it was improved in the paper by these three people, that actually for any totally regular matrix, you also have this. May I actually ask maybe anyone to mute him or herself, because there is some background noise. Thank you. You can do this logarithmic factor, and you actually need untouched minor argument. That's what I think I will have time to show. And you also need to use some results in extremal graph theory, and it will give you this extra factor. But that's basically it. That's the limit of our knowledge. So let me now also show a couple of relaxations. The first one, which was also studied by at least several people, is that, all right, so our matrix, assume that our original matrix A is, say, Rademacher matrix plus minus 1 matrix, then should you apply big changes, or you can look at other norms, not only zero norm, but you can also, for example, bound the number. So each is simply the maximum absolute value of entries. Assume that you not only have a budget on your entries, but you also are not supposed to make very big changes. Then turns out that you can do much better. So in all, there are two results. It is from the same paper by Boris and mine. So, for example, if theta is constant, if you are allowed changes of a relatively small size, then you get the optimal bound, and you can do even better in the regime when the number of changes is not exactly constant, but something which is bigger than constant. That's an improvement on this result. So, and that's one relaxation. And let me very briefly mention another popular theme. And this popular theme is, in fact, where is it? We now play around with this notion of explicit. I did not specify what it means explicit. It's in a good sense, or you can say that it's explicit if you can construct entries of your matrix in polynomial time. You can apply any of these definitions. It's one of those things you really don't want to define, but everyone knows it when you say it. And there has also been an interesting line of research relaxing this notion. For example, let's consider Vandermonde matrix. Then this Vandermonde matrix, it is described by n values, not n squared as an arbitrary matrix, but by n values, x1, x2, xn. And you can ask the same question. For example, over infinite field, let's take generic Vandermonde matrix. So it has now transcendence degree over the ground fields, not n squared by n. For example, Satya Lokam proved that it will also be rigid, maximum. So it is very good bound on rigidity.
And what is a big R here? Big R.
Rigidity. Rigidity.
Rigidity.
Rigidity. Yeah.
Okay. So
V is Vandermonde. That's so I used V because it's Vandermonde. It's the same as before, RRA. And there also have been recent results. Again, I would prefer not to go into details because I will have to introduce too many different concepts. So you can relax the notion of explicit in many different ways, and you will get rigid matrices. For example, sub-exponential time, polynomial time hierarchy. You can apply something else, more even fancier complexity classes. It's a good line of research. So, all right, now, except for these results, all other results are sort of ancient, or at previous century or almost previous century. So the question, of course, is why? Why I am doing it here? Because, well, first of all, I obviously want to draw attention to the fact that it's a major open problem which is out there to be solved, but also it is the result that Yuri mentioned at the end of his talk. And in the remaining time, I will try to give some ideas of its proof. So, and it is essentially, well, it was extremely surprising because our common belief for all those 30 years was that Hadamard matrices, and in particular Sylvester or Walsh-Hadamard, whatever you call it, matrices are hard. It's just that we are stupid and cannot prove it. So basically, this result, it said that after all, maybe we are not as stupid, or at least we are stupid for different reasons, because we were trying to solve something which cannot be solved. Turns out that in Sylvester matrices, at least, well, the result does not apply to arbitrary Hadamard. You really need the structure that I will try to explain. It is not rigid. So what it means, assume that I give you this budget on the number of changes, and so the 1 plus epsilon, where epsilon is any constant, then you can reduce your rank, the rank of your matrix, not only to n over 2, you can reduce it even below that. You can reduce it by n to the minus delta, where delta is something which depends on epsilon, but it's also bigger than 0. So they are not rigid in the valiant sense. So as I said, that's what I will try to do in my remaining time. So let me show just very briefly one other result, very interesting result, because if you have a matrix defined over some field, for example, or right, let's ask very simple question. If you have a Rademacher that is plus minus one matrix, then it is defined over the rationals. Is its rigidity over the rationals and over the complex numbers is the same or not? Well, turns out it's a very nice result, not very difficult, but still very nice. Turns out that at least sometimes it can change. So if you extend your field from the field of definition of your matrix A, then really the rigidity can grow at least a bit. So thus the ground field is important, and this is my last slide. So the open problem here is obvious, and it's like good wine, which every year it's getting more and more important because many people tried it and no one succeeded. So those other matrices that I showed in my talk, Vandermonde and Cauchy matrices, are still in the business. Their results does not apply to these matrices as far as I know. For applications of communication complexity, you probably can even apply Sylvester matrices, but of course, after this shock, now people are not as bold to make conjectures. So sometimes, somehow, it's up in the air. There are many smaller open problems in the area. So, and it's the last thing I want to say on my slides is that when I was preparing this talk, then there are several good surveys on matrix rigidity, and somehow this is the one I liked the best, and it was the most useful for preparation of this talk. So it does not mean that the talk is over. Let me. It does not mean that the talk is over. It means that my slides are over. So it's very good time to ask questions, because in my remaining something like 15 minutes, I will try to show you some details of two proofs. Any questions? The slides will be gone.
May I ask, Sasha? It's not maybe standard question, but just a little bit of propaganda. Under influence of this computer science, Yura and I differently, we consider approximation in metric of measure, conversions in measure. So discrete version. It's clear what you just take metrics with the conversions in measure. So integral of divided by 1 plus f. So matrix is rigid. It cannot be approximated by metrics of small rank, changing a little bit of elements, a small quantity of elements. We have some estimate now, stronger quantity when we approximate in this metric convergence in measure. And of course, if we have lower estimate for this quantity, we can say something about standard rigidity. So my question is, it makes sense for computer science to consider this metric instead of this changes of elements, uncontrolled? Because this metric is very good control arbitrary changes of elements. But
Boris, if you ask me personally, then I am a mathematician. It obviously makes sense to me for intrinsic reasons. If your question is whether it might help to finally make progress on rigidity, then the honest answer is we don't know. We don't know what will help to make the progress. It might be this way.
This metric connect function theory and computer science because.
Yeah.
So I'll send you this note. It's not big deal, but maybe in negative result you can prove not just your rigidity, but our rigidity when you change in.
What do you mean? What do you mean by negative?
I mean the low estimate. So the metric is rigid in your sense.
Yeah.
And maybe it's also rigid in our sense, which is stronger. So we cannot approximate and measure distance by the metrics of small rank.
Okay. So I should look at the details because it's clearly it's not a generic question. I have to
Okay, I'll send you the note and maybe.
Yes, please.
Thank
Right.
you.
So any more questions? Right. Good. Then let me now start something new. Can you see my whiteboard?
Yep.
Yeah.
Let's hope it will work better. So I will basically, the first thing, let me see my marker. The first thing I want to do is totally, how did I call them? Totally regular, right? Totally regular matrices. Let me show this observation by Nissan and Grigoryev because it will take 1 minute and it's a good warm-up. So I have a matrix A, which is totally rigid. A is totally rigid. It's a matrix. And I want to prove lower bound on rigidity like that. That's what we want to prove. So, and the trick is extremely simple. Actually, let me make it even more precise here. It is m squared divided by 4r squared. And the trick is very simple. So I will just divide my matrix A into blocks of size 2r times 2r each. So then I will have as many blocks n squared divided by 4 times r squared different blocks. And since my matrix is totally regular, every block has full rank. Therefore, if I want to reduce even if I want to reduce the rank of even every block, any block A, in A, then I should change at least R entries in every block. So answer, now you multiply it here by R and you get your bound. So very simple, it's warm up. Any questions? Good, and now in my remaining 7 minutes, I will show you at least, I will tell you at least something about Ullmann-Williams results. I will get you at least, well, it's computational, it involves some nasty computations, but general idea, I think I will be able to do here. So what we now have, we have Walsh-Hadamard or Sylvester matrix. Let me write it down like that. So rows and columns are indexed by strings, Boolean strings of length n, and Hn of xy is the inner product. So the first idea is that actually, since we have central limit theorem, etc., for example, if I take a random entry in my matrix A, if I pick up string x at random, and if I pick string y at random, then we have very good idea what will be the range of this intersection, because this is simply intersection. If I look at x and y as sets, it is simply intersection x and y modulo 2. When I view them as sets, then we have a rather good idea what will be the size of this intersection. And after we have this idea, then we can somehow postulate that the intersection of x and y, the size of this intersection, I mean, it belongs to some interval between, say, n and b. Because entries where it is not the case, they are sort of exceptional, right? We can ignore them because it's rigidity. We don't care about their values, they will be changed. So it is when you really start implementing it, then it turns out to be way more difficult than it looks here. So you have also to control sizes of x and y themselves. You have to perform certain calculations, etc. It will be not as simple, but for my 4 minutes, I will just assume that that's what we are doing, that we can assume that the size of the intersection x and y is controlled, and then we can apply the following nice trick that they discovered. First of all, I apply interpolation theorem. So here are my products, x, y, y1, x, and yn. X and y are Boolean strings. I just take these products in every particular coordinate. Then let me denote this intersection, the size by z, then z is just x1, y1 plus x1, yn. Okay? So the first thing we do, we apply standard interpolation theorem, and I find univariate polynomial q of z, which takes the right values. So it is a plus 1, b, and the values are it is basically a modulo 2. They alternate. It's plus 1 minus 1 plus 1, etc. But we are not interested. I mean, we don't care in the green part. I just taken univariate polynomial that interpolates this thing of degree at most b minus y, or degree is at most b minus a. And then I plug my value for z into this polynomial. And now I look at this thing as a matrix. I look at its at this thing as a matrix of my polynomial MQ. Well, defined in the obvious way, it is just the value of the polynomial. So then turns out that, again, calculations are a bit unpleasant here, but they were checked many times. Turns out that the bound on the degree of my Q allows you to control the number of terms, sparsity of this polynomial. You can control it. And
I'm sorry, MQ, what is it? Big M.
big N is 2 to the N.
What? No, M.
Oh, matrix. It's a matrix defined like that. I look at my polynomial and I view it as simply a matrix. So, and since Q has low degree, then this thing will have low sparsity. It will not have too many terms. And for every individual term, we get a rank 1 matrix, right? Because variables are separated. It will be a product of something in X and something in Y. It will have a rank 1. Therefore, you can control the rank of this matrix, and it will be precisely the lower rank matrix that approximates our original matrix H. So again, that's the basic idea. Implementation is technically you have to compute a few things, but it's a major result, and we'll see what will happen now in the area. Again, it's a beautiful area, and we have to solve it. It's really affront into our face. It's a challenge. Right, good. I think my time is up. Thank you very much for your attention. Let me save my slides in case anyone will be interested. And thank you. I will now take questions and I can return to, yeah, thank you.
Thank you.
Thank you.
Let me return to my slides in case there are any questions. Mm-hmm.
So can I add a comment?
Mm-hmm.
So, the last result is exactly that I wanted to mention, but I have no time. So it's good luck that the
This one
on that MQ matrix are good. So it has not so large values, and in fact it approximates in LP every row of Adamar matrix. So
Yuri, what result are you talking about?
the last.
This one. This one, yeah.
No, he's talking about your very last result.
But
this one.
No,
On a whiteboard.
and Williams.
But the last result on the whiteboard was this one.
Yes. So here we have an approximation that is controlled by, we can control not only the number of changes and tries, but the volume of the changes.
Yeah.
So it gives approximation in LP for each row. But in other cases, the constructions of non-rigidity, for example, for Fourier matrix, are very, very complicated, and we can't control the volumes. This is a problem. So, and one another comment, Boris Sergeyevich mentioned the L0 metric, and the rigidity in L0 is a stronger notion. So the matrix can be approximated in L0. This is a stronger. But if we consider L1, the notion of L1 rigidity, so when the average of the differences between your matrix and approximation matrix is high, this notion is, well, maybe it's related, but it's different. Maybe do you know some results on L1 rigidity where the matrix can't be approximated in L1?
No. I thought about it, and it very much looks to me now, if you talk about L1, it very much looks to me like compressed sensing, but I don't know of particular examples.
More questions?
This is sort of L1, right? Or if you multiply 0 and infinity, you will get 1, correct?
Not
Oh, I'm here.
Yeah.
Yes, but morally it is the case because if it is S and it is theta, then L1 is bounded by theta times S.
Yeah. In one side, yes, of course.
What I'm saying is that if you look at our results, then maybe you can get something out of it in the opposite direction as well. But I did not try it.
But metrics of measure conversion measure could be interesting for.
Yeah, certainly.
Okay, thank you.
So if there are no questions, we have.
Maybe last. We also study, Sasha. We also study your paper about quantum. Maybe Yura could explain better.
Quantum, yeah. So it's just I can easily connect it to Yuri's talk because the lower bound for the quantum complexity he mentions, it was the first bound, and it is good, for example, for our good friend Sylvester. You can bound Sylvester for it.
No, I'm speaking about your paper in this list.
Yeah. I'm coming to it.
We tried to prove it by our method, but it was not the case. We could till now.
Yeah. That's what I mean, because rank epsilon is, if you look at the disjointness problem, then this turns out to be much weaker, and you have to apply different methods.
Yeah.
So much more analytical, well, as you know from my paper, and much more advanced.
Yeah. But in any case, it's very good notion for both, for function theory, for computer science.
Yeah, it's an excellent connection, and many results in the area are quite analytical. So
Kolmogorov was great.
Yeah.
In introducing. Okay, thank you.
Yeah, thank you.
Okay, so